At hypersonic speed, air can become one of the most dangerous parts of the journey. But it does not literally turn into a solid wall, and the heat does not always reach 5,000 degrees. The real story is more interesting. Hypersonic flight usually means traveling at Mach 5 or faster. At that speed, pressure changes cannot move ahead of the vehicle fast enough to let the air adjust smoothly. Instead, a shockwave forms. Imagine walking through a crowded hallway. People see you coming and step aside. Now imagine moving so quickly that nobody receives any warning. The crowd must react suddenly. Air behaves in a similar way. The molecules do not remain trapped against the vehicle. They pass through the shock, slow down, become compressed, and then flow around the body. Across that very thin shock layer, pressure, density, and temperature rise sharply. Part of the air's organized forward motion is converted into internal energy. In simple language, the air loses speed and becomes hotter. A bicycle pump gives us a useful comparison. When you compress air quickly, the pump becomes warm. Hypersonic compression is far more intense, especially near the front of the vehicle, where the flow is forced to slow down and change direction. But this does not mean every vehicle flying at Mach 5 creates the same temperature. Heating depends on speed, altitude, air density, flight time, and the shape of the vehicle. A craft traveling briefly through thin air may face very different conditions from a spacecraft returning from orbit at several kilometers per second. At the most extreme re-entry speeds, the air can become hot enough for oxygen and nitrogen molecules to break apart. Under even more energetic conditions, some atoms lose electrons, and part of the gas becomes plasma. That is why saying Mach 5 automatically creates 5,000-degree plasma is misleading. Now comes the strange engineering question. Should the nose be sharp or blunt? A sharp nose looks like the obvious choice. It can cut through the air with less drag, but it also keeps the shock wave close to the surface and concentrates heating into a small area near the tip. A blunt nose behaves differently. It creates a detached bow shock that stands a short distance in front of the vehicle. The hottest shocked gas is then separated from the surface by a wider shock layer. The gas still transfers heat to the vehicle. The rounded shape does not create a perfectly cool bubble or an invisible force field, but it can reduce the peak heating reaching the surface while also creating more drag, which helps a returning spacecraft slow down higher in the atmosphere. This counterintuitive idea transformed spacecraft design. Early engineers might have expected a long, needle-shaped capsule to survive entry best. Research led by H. Julian Allen and Alfred Eggers showed that a blunt body could manage the heat more effectively. That is why capsules such as Mercury, Gemini, and Apollo returned with broad, rounded heat shields facing forward. But there is an important difference between a re-entry capsule and a hypersonic aircraft. A capsule wants high drag so it can slow down safely. A hypersonic aircraft may need lift, low drag, engine airflow, and the ability to cruise or maneuver. For that reason, many hypersonic aircraft still use relatively sharp noses and leading edges. Engineers protect these areas with heat-resistant materials, insulation, special structures, or active cooling. There is no single perfect shape. The best design depends on the mission. Heating also does not come only from the shock wave. Along the surface, a thin layer of air called the boundary layer is slowed by viscosity. Energy moves through this hot layer toward the skin. If the boundary layer becomes turbulent, it mixes more aggressively and can increase surface heating. So engineers must manage shock heating, boundary layer heating, pressure loads, changing air chemistry, and materials that become weaker when hot. Some spacecraft use ablative heat shields. These slowly char and wear away, carrying energy with the lost material. Others use reusable ceramic tiles, heat-resistant metals, or cooling systems. The goal is not to defeat physics, it is to control where the energy goes. So at hypersonic speed, air does not become a literal wall. It becomes a rapidly compressed, extremely energetic flow that can heat, push, and chemically change around the vehicle. And the blunt nose is not a magic shield. It is a clever way of moving the shock wave, spreading the heating, and helping certain vehicles survive one of the most violent journeys through the atmosphere. The strangest part is that sometimes the safest way to travel faster is not to look sharper, but to face the air with a wide, rounded shield.